This is the third video in my series on cohort studies. The first two talked about just an overview of cohort studies, and then there was one on retrospective versus prospective cohort studies. And this one's just going to be focusing on how to analyze data that originates from cohort studies. So just a review of the basic format that all cohort studies have in common, basically. I guess prospective cohort studies. Retrospective shares this in a way that is mostly working with medical records rather than real time, but the principle is the same. So you have this population of people, you figure out who's disease positive, and you eliminate them basically from being included. And that's because we're only interested in incident cases. That's people who go from disease negative to disease positive during the study period. So we have this population of disease negative people, and we take a sample of them, and then we figure out the exposure status. That's the baseline exposure status of everyone. And we separate them into exposure positive and exposure negative cohort. Then we follow them basically from some baseline over time, for example, 5 years, and figure out how many people became diseased in the two groups and see if disease was more common in one group or another. For example, if disease was more common in the exposure group, or like the exposure positive group, then that would be a little bit of that would basically be some evidence that exposure is causing the disease. So this is just kind of a simplified idea. I'm going to separate this further just quickly to talk about incidence density versus cumulative incidence, just because that has a little bit of influence on how you will analyze the data. So to talk about that, I need to first kind of mention the difference between an open and a closed population, which has some implications at mostly how rates are calculated and whether a rate can be calculated, how time is handled or not handled, and whether exposure status is allowed to change, so whether someone can go from exposure negative to positive or vice versa. So a closed population is the simpler of the two. So basically, people would start out, this is 4 people, say maybe the first 2 are exposure positive, second 2 are exposure negative or something. But as far as just describing a closed population, we don't really need to think about exposure at this point. But basically, everyone starts out disease negative, and they're followed for 4 years, and then you count, like, basically who got the disease and who didn't. These blunted lines are people who didn't, these dots are those who did. And event is just kind of a generic term for an outcome, which is a generic term for a disease. So basically what makes this a closed population is no one left early and no one was added late. And we would calculate cumulative incidence from this by doing the number of events that occurred over follow-up, so 2, over the number at risk, which is 4. So 4 people were initially at risk, and 2 events happened at some point in the 4 years. 2 didn't. So basically, 2 out of the 4 people initially at risk got the disease for a cumulative incidence of 0.5. And that doesn't have units, that's just a proportion. Also, I showed these happening at the end, but basically it could have happened at any time during the follow-up. Open populations are a bit more realistic, so basically this is an open population that's showing some right censoring. So these people with an arrow, they stopped, their follow-up basically stopped, not because they got the disease, but for various reasons, like they stopped showing up to their appointments or died of something else besides the disease of interest, or got to the end of the study and didn't have the disease by the end. There's also left centering, where people are recruited over time, and basically what this amounts to is this open population where like people are being added and late and leaving early, and it's much more realistic, and basically we're showing their follow-up time as a function of calendar time. So this allows us to calculate incidence density, where before, if you recall, for cumulative incidence, the denominator was number of people at risk. Well, now it's person years of observation at risk. So it still has people, but now it's people and time, basically. So what I mean by that is you would count up the amount of time contributed by each person. Like 1 year from this person was followed for 2 years, this person for 2, and same with this person, and you add that up, and basically you can find the incidence density, which is 2 events over 7 person years being followed. And this can be more than one. It's a true rate because it has time in the denominator, And another thing that's cool about this is people's exposure status can change. So I know exposure isn't written here, but just picture that this person was a non-smoker and then at year 1 they began smoking, and basically they can contribute some time in both exposure groups. So person time plays a role in a few types of analysis. So survival models are a common one. I have a video on survival analysis if you're interested. Basically, there's 2 major ways to analyze this. Kaplan-Meier is kind of like the equivalent of like a bivariate analysis, where you're basically just like looking at 2 treatment arms and comparing their time to death, basically, and seeing if survival's longer in one of the arms. Cox proportional hazard is the much more commonly used one, because that's like the regression for survival analysis, where you can control for as many confounders as you want. So basically, with time to event analysis, you're logging how long it takes for everyone to go from like initial observation to death, and figuring out whether like the survival function is steeper downwards for the exposure group, and that would be indication that exposure is leading to death. It's making your survival less likely over time. So survival analysis really makes use of person time. Poisson regression does as well. And survival analysis has has a hazard ratio as its measure of effect, which can basically be interpreted as a relative risk. Poisson regression is the basic regression that generates rates, and it's useful in 2 scenarios, both of which typically integrate person time into its calculations. So Poisson regression can be used to handle counts. So if it's like some event that can happen more than once over a follow-up period, like I don't know, like if you're following for several years and it's the amount of time someone catches a cold, that's an event that can happen multiple times. And it's also good for rare binary events, and it has person time really integrated into its analysis, and basically allows the calculation of a rate ratio, which can be interpreted as a relative risk. So I'm just going to go over like this decision tree for how to analyze cohort data. It's the best I could come up with, and there is a possibility that there might be some of it might be up for debate, but I'm feeling pretty confident about this. So the 4 ways that you can basically separate types of cohort data, there's when the outcome is continuous, like if we're measuring cholesterol concentration after some period of time. There's time to event, which is like survival analysis. Categorical outcomes, like a disease happens or it doesn't. And a count, so like the number of times an outcome happens to an individual. So just starting with the easier ones, for a continuous outcome, linear regression is typically what you would use to analyze that. For count data, you would typically use Poisson regression. If there is time to event data, what you use depends on whether you hope to control for multiple confounders, or whether you have just one confounder or no confounders, so you're just looking at treatment and disease. So if you have one or no confounders, Kaplan-Meier is a useful one. But if you have multiple confounders, Cox proportional hazard is the better option. And I think technically Cox proportional hazard can handle this situation as well. For a categorical outcome, this is the most elaborate tree, basically. The first node on this tree that I came up with was the number of categories the outcome has. So let's just say like a binary outcome, like you're diseased or you're not. But there's also situations where the outcome has more than 2 categories. So that's something like if the outcome is like high, medium, and low. So I'm just going to start with this one. This can be sub-specified into whether, like, let's just say there's 3 categories to the outcome, whether that's ordered or unordered. So an example of ordered is, like I just said, high, medium, and low. And you can use ordinal logistic regression. If it's unordered, I guess like 3 races, they don't have a natural order to them or something, that's a stupid one because that's not an outcome. But basically just a categorical a categorical variable with more than 2 categories, but there's no logical order to them. In that case, just multinomial logistic regression is what you can use. The next category as binary outcomes. That's more commonly what you're going to be using, just disease or not, basically. And the analysis you do kind of depends on whether the outcome is rare or common in the population. So if it's rare, then Poisson regression is probably the way to go, and you can use that to estimate relative risk. It's possible you could use logistic regression. Poisson is typically what people use. When I think of use of logistic regression, it's usually in a case control scenario, but I think you could probably use logistic regression here, and because the disease is rare, your odds ratio would be your measure of effect, and that could maybe you could argue that could be used to estimate or be used as an estimate of the relative risk. If the outcome's common, I guess the next thing you consider is whether there's few covariates or many. So that's similar to here, whether there's one confounder or many. If there's few, log binomial regression can be used. They're good with common binary outcomes and can be used to analyze this kind of data. But when there's many covariates, log binomial might not converge. The model might not work, and in that case, you can do modified Poisson, which basically is able to like the reason Poisson can be used for rare outcomes is because even though it's not a count the way Poisson is typically used, this distribution starts to resemble a binomial distribution the rarer the outcome is, but as soon as the outcome becomes common, it starts to basically a binomial outcome starts to resemble a Poisson distribution the rarer the event is. But if the event is common, then Poisson is not, some of the assumptions of the Poisson distribution aren't met. So you can use a modified Poisson regression, which basically is doing the same thing but permits the outcome to be more common. And in this case, you could probably also do logistic, but it's even less applicable than this other scenario I was talking about, where now the best you can hope for is for the outcome to, for the measure of effect to be an odds ratio. And I don't know, people don't really like odds ratios. They're not that bad, but best case scenario for an odds ratio is that we can pretend it's a relative risk if the disease is rare, basically. That's kind of the best case scenario if you're an odds ratio. And that's basically it.